Welcome back. In this video, we are going to discuss in particular a bit more detail on the frequency response function, and then we are going to discuss also on how to sketch frequency response function either with the help of computer or how we will sketch it by hand. In this video, these are the few topics that we are going to cover. In the first few slides, we will discuss a bit more detail more on the fundamental of Bode plots, and then I will share with you how the Bode plots of a few simple dynamic system will look like, also on how to sketch it in a faster way, and then I will just give probably one or two slides on the example on how to derive the Bode plots using MATLAB. Let's consider again this block diagram representing a simple dynamic system with a transfer function of GS, where a harmonic input xt is given to the system, where in turns the system will respond by having a output yt there. How to analyze yt, we have already discussed it in the previous video. Technically then, using Laplace transformation, we can analyze the response in Laplace domain ys by multiplying gs with the input x in Laplace domain as well. As the Laplace of sine omega t is equal to omega over s squared plus omega t, obviously then the response in Laplace domain ys will be equal to the transfer function gs times omega x over s squared plus omega squared. Applying the partial fraction expansion, we have already discussed it also in the previous video. I can expand this equation of yt into this following line, consisting of few terms like this, where the first two terms are associated to the input, as we have omega here, and then the remaining terms from the third terms onwards are associated to the poles in the transfer function gs. We also have discussed it in the previous video that these terms, the third terms onwards, are associated to the transient response, while the first two terms that contains omega here, where omega is the frequency of the excitation, the frequency of the input, are associated to the steady state response. Finding the coefficient k and k star, you can refer to the previous video on how to derive k and k star. We can conclude that k will be equal to minus x gj omega over 2j, and k star basically is just the conjugate of k. Having this k and k star, we can complete the ys. The ys will look like this if we only consider the steady state part, and then after we analyze ys there, we can easily conclude that the ratio of ys and gs is equal to j omega, or in this case then, if we are looking at the frequency domain, the ratio of j omega over x j omega is equal to j omega. If we plot the magnitude of j omega, and if we plot the phase of GG omega, we will get what we call as a Bode plots. So Bode plots consist of two plots, the magnitude plot, which represent the ratio of output and input, or in other words, the ratio between the amplitude of the output and the amplitude of the input, and a phase plot that tells us the phase difference between the output and input. We have already discussed also in the previous videos that this magnitude plot and phase plot are normally presented in a semi-log papers. The magnitude plot normally is presented in dB scale, while the domain, the frequency, is typically shown in logarithmic scale. That's why we normally use a semi-log paper, while the phase plot is presented in linear scale as usual, but we still use frequency in logarithmic scale for the horizontal axis. Therefore, typically Bode plot will look like this. As you can see, the horizontal axis are frequencies in logarithmic scale, linear scale for the phase plot in vertical axis, while the vertical axis for the magnitude is the gain or the magnitude in dB scale. In some Bode plots, you might see this kind of features. Not all Bode plots, but some of them you might see this kind of feature. A pretty flat line on the magnitude plot at the low frequency, and also flat line at the low frequency of the phase plot. You might see some dips in the magnitude plot. You might also see some peaks in the magnitude plot. Not always, but in some Bode plots you might see this. What these features tell us? The first one, the constant magnitude at low frequency. This will tell us, sorry if I can say further, you might also have a constant phase plot at low frequency, but either magnitude or phase plot which give a constant line at low frequency, this will tell us the bandwidth of the system, which literally means the wider this band or the higher the bandwidth, the faster the system will respond to the input. The second feature here, the peaks here, normally associated to the system poles. But as I have already mentioned before, not all Bode plots will have this kind of peaks. It doesn't mean that it doesn't have poles. So if you have peaks, then the peaks here associated to the system poles, but not all poles will manifest themselves in this kind of peaks. You might also have a dip like this, which is referred to where the frequency where we have dip here is referred to anti-resonance frequency. This will tell us the zeros of the system. Same thing like similar to system poles. You might not see these dips. It doesn't mean that the system doesn't have zeros. Okay. So these are what we typically see in Bode plots. Let's take an arbitrary example here. I have Bode plots of a system that look like this. The upper one is the magnitude plot, the lower one is the phase plot. As you can see, again, the horizontal axis is a frequency in logarithmic scale. The vertical axis of the magnitude plot is the magnitude in dB scale, while the vertical axis of the phase plot is just the phase angle in linear scale. So if, let's say, to this particular system, to this system that has this kind of Bode plots, I give an input, a harmonic input with an amplitude of 5 and frequency of 0.01. By just simply looking at the Bode plots, I can estimate the steady state response. How do I do that? It's pretty simple. I just simply have to identify the frequency of the input. It's 0.01. That is the frequency of the input, 0.01. In logarithmic scale, it will be this one, right? 10 power of minus 2 is 0.01. And then what next? I just simply have to identify the magnitude and the phase. So, okay. If I look at this, probably roughly I can estimate that the magnitude at that particular frequency, at frequency of 0.01 radian per second, is equal to 40 dB. 40 dB in decibel scale corresponds to 100 in linear scale, right? 20 log magnitude is equal to 40, okay? Log the magnitude is equal to 2, that means the magnitude is equal to 100. And then accordingly, the angle at that particular frequency, let's say it's equal to negative 60 degrees or negative pi over 3 radian. Having this information, I can estimate the response in a steady state condition, where the response here, the amplitude is amplified by this magnitude. Since the original amplitude is 5, so now the amplitude of the response at the steady state condition will be equal to 5 times 100, while the phase, according to this phase plot, will be lagged by 60 degrees because we have negative 60 degrees here. Therefore, the harmonic response will be the amplitude will be equal to 500 and the angle will be lagged by 60 degrees. So the response, then it will be equal to 500 times sine 0.01 t minus 60 degrees or minus pi over 3. This is how Bode plots from a frequency response function will help us to estimate roughly the steady state response of the system. In this plot, I will give an illustration, the relationship between frequency response function to the transfer function. So let's say we have a transfer function in our dynamic system that looks like this. As you can see here, we have 2 zeros and we have 3 poles. For instance, if we want to find the magnitude of g omega at this particular omega, as well as we want to find the angle of g omega at this particular omega. So what do we have to do? What is the relationship between g omega and gs, the transfer function gs? The relationship will look like this. The frequency response function GJ omega at this particular omega frequency is equal to K times the factors from this pole, from this zero to that frequency. So let's say if this is Z1, so as Z1 is the factor from this zero, to that particular frequency, times again the factor from 0Z2 to that particular frequency, divided by the factor from pole 1 to that particular frequency, times factor of pole 2 to that particular frequency, times factor of pole 3 to that frequency. Okay. In the polar form, of course, this factor, let's say factor of Z1, I can represent it into this form, right? Factor that point us from one point to another point here is equal to the magnitude of the factor itself times the angle representation in complex coordinate system like this, right? This means then the magnitude of GJ omega consequently will be equal to K times R1, the lowercase r1 times lowercase r2 times capital R1, capital R2, capital R3, where these are capital R1, 2, 3 and lowercase r1, 2. These are the norm of the factor. If you look at this, if I go back to the previous slide, R1 is the magnitude of the factor from Z1 to omega. Same thing, the capital R1, let's say, is the length of this factor from pole P1 to omega. Okay, so that's what the relationship of magnitude G J omega to the transfer function. If we express it in a logarithmic scale, of course, logarithmic of magnitude G J omega will look like this: logarithmic K plus logarithmic lowercase r1 plus logarithmic of lowercase r2 minus logarithmic of capital R1 minus logarithmic of capital R2 minus logarithmic of capital R3. Okay. This means also that a magnitude can be represented as a summation of the logarithmic of the DC gain there plus summation of all of the logarithmic of the zeros factors there minus the summation of the logarithmic of all of the pole factors, right? What about phase? Referring again to this slide, same thing to the phase. For the phase, then the angle of GJ omega technically will be equal to angle of this plus angle of this, angle of the first zero plus angle of the second zero minus the angle of the first pole minus the angle of the second pole minus the angle of third pole. Okay, again then this is the relationship of the phase of GJ omega to the GS. If we want to represent this in algebraic sum, then The angle of GJ omega will look like this. Just simply the summation of the angle of all of the zeros factor minus the summation of all of the angle of the pole factors, right? Let's take a look on this simple illustration. I have a system with a transfer function GS where the DC gain is K. I only have one pole, I only have one zero at negative Z and one pole at negative B here. If I want to evaluate the magnitude of GJ omega and angle of GJ omega, what I have to do, the magnitude of GJ omega technically is equal to K times lowercase r, where lowercase r tells us the norm of the factor from 0 to the particular frequency of interest, divided by capital R, where capital R is the norm of the factors that point from the pole to the frequency of interest. Well, the angle of J omega technically is just simply the angle of the factor of the zero minus the angle of the factor of the pole. Okay,